The recording has now started. Okay, so today we're going to be talking about basically advanced dplyr functions. So 2 weeks ago, we got started with dplyr, where we learned about mutate, filter, select, all of these base functions that make your life a lot easier when you're looking at data, manipulating data, not in a bad way, but in a good way, which we call data wrangling. And today we're going to go a little bit farther with some new developments in dplyr that have come out within the last year. So when you're looking for help on these subjects, sometimes it's kind of hard to find if you're Googling for Stack Overflow, etc. Because this is all part of dplyr 1.0, which I think came out in June. And they're really useful, but as I said, they're new. So there's unlikely to be any bugs, but there could be. So we're going to cover a few different functions today. We're going to cover across, which is one of the new ones, case when, which is not a new one, but it's still more advanced for if you're doing mutates. We're going to cover how to change row names to column names, and we're going to cover how to get unique values from a column. And then finally, we're going to work through something called row-wise. So we're going to work through all of those in a lab like we normally do. So I'm going to start sharing my screen so we can start learning. Okay, let me get everyone's faces nice and big, which I try to do. There we go. Okay, so as you can see here, I've just got a simple R Markdown document that I already just started and pre-populated with the 5 main functions we're going to be learning today. And we're probably going to spend the most time on across and row-wise, which are kind of, we're sandwiching these other shorter ones in between them. So we'll get started first with across. So you may have realized if you're trying to do the same function multiple times across multiple columns, it was very repetitive. So before I get too ahead of myself, I need to load my data and the tidyverse. So as always, we're going to load the tidyverse. And then from here, once I load that, today we're going to be using a data set called Star Wars from the tidyverse. I think we used that for like 5 minutes at one point. Still loading. There we go. I don't know why it's so slow sometimes. So, and then we're going to load the data called Star Wars, and that comes from the dplyr package, which is loaded with the tidyverse. So if we look at Star Wars, we can see we've got 14 different columns, and this is all data about characters from Star Wars, trying to keep it fun, you know? So we've got Luke Skywalker, C-3PO, etc. We've got their height, their mass, their hair color, skin color, eye color, birth year, sex, gender, homeworld, species, what films they were in, I think what vehicles they're associated with, and what starships they're associated with. A lot of those we're not going to be using, but it's useful to know what's kind of in those variables. So as always, my favorite is glimpse. So let's jump into that and we can see what types of all the different columns they're associated with. You can see some of these are a list column, which we haven't seen before, and we really won't work with a lot in this class. This just means it's kind of like a JSON file, if you know anything about JSON, where we've got everything as a row, but sometimes that row has sub rows in it. And I can show you eventually how to unnest those, which is the function you use to make them not be a list, make them have multiple rows per item. But for now, we're not going to deal with that. We're going to get back to what I was trying to say. So sometimes when you have your Star Wars, I'm going to spell that wrong every time, I feel like, data set, and we want to summarize, let's say, both the height and the mass of everyone. So let's say we want to take the height, mean is the mean of height, and I already know there's NAs, so let's do an NA remove equals true. And then I also want to take the mean of the mass, which is their weight. Equals mean of mass NA.rm equals true. So if I want to do that, you can see how this would quickly get really repetitive, and I would be keeping writing out the same thing over and over and over. If I also wanted to get the minimum, the maximum, the third quartile, anything like that, I'm going to have to add a new line for every function, for every variable I want to do. And as you can see, as I was typing, I was already making mistakes, and that's really easy to make mistakes as you're typing. So I'm just going to really quickly show what a cross is and what it does, and then we'll get into some more details. So Star Wars, and here I would instead say summarize across height through mass. I believe they're in the same spot. And we would say mean. Let me try that, make sure it works. It does not, because we did not do NA remove equals true. And so I'm just going to explain each component of this, and then we're going to go into a lot more detail. So here we're saying summarize across these variables. So do this, a function we're asking for across multiple variables, get the mean, this is the function, and then here's some extra options for that function. There's multiple ways, as with everything we've learned, to write this sort of function. But if I want to be very explicit, I can say calls, so dot calls and then dot fns. So this can make it a little more explicit that these are the functions and these are the columns that I want to do these functions to. So right now what we're doing is saying, take this function and apply it to multiple columns. I can extend that even further and say Star Wars summarize across is numeric, and that will apply it to everything that's numeric, and then take the mean and then NA remove equals true. Feeling it was going to error. Sometimes is numeric has parentheses, sometimes it doesn't. Okay, this is why we follow your lesson plan and we don't go off book. Okay. Predicate functions must be wrapped in where. So here we actually have to say where is numeric. Okay, so this would say for all of the variables that are numeric, do this function. So in this case, it was height, mass, and birth year. Now let me go back to the actual lesson plan so I stop doing random things that were not planned ahead of time. So this is really useful, as you can imagine, because oftentimes you have a lot of different variables you want to work with and you don't want to keep repeating yourself. One really good thing, or one important thing about having replicable code, about having good code, is not repeating yourself too many times, because every time you repeat yourself, you're going to add an extra comma, you're going to have a spelling error somewhere, and that's where you get bugs. And so if we repeat ourselves less times, things can be more efficient, our code is cleaner, etc. So we can obviously do this with other things besides mean. Anything that would normally have a parentheses at the end of it, like that, we could do. So here we could do median instead. We could do min. If we want to do more than one of these at a time, which is also me jumping ahead in the lesson, I'm just going to copy and paste this to show you how you would do more than one of these at a time. More than one function. So if I wanted more than one function, I have to use a list. And so here I could say list, which is very similar to when we do a C. Actually, both of those work, but there's an advantage to using a list. So I'm going to use a list and then show you what that looks like. So there we go. My errors went away because my parentheses are now balanced. Now, if I run this, you can see I'm getting my min and my max, and it's automatically generating height 1, height 2. This 1 and 2 are the number of functions. So the first function was min, the second function is max. Mass 1, mass 2, birth year 1, birth year 2. Oftentimes 1 and 2 is not great for our coding, because then later on we're going to look at our variables and we're going to have to say, which one did I do when, which one was first? So this is where the list comes in, because we can use a named list. So kind of like when we were creating tibbles before, we can add basically a name to the function. So the function's second, and this is a name. So I could add a lowercase here. I could add anything that I want to be the new name for this. Like I could say maximum, even though that's not the name of the function. I could make that the name of the function I want, minimum. So now when I run this section here, I'm getting height minimum, height maximum, mass minimum, mass maximum. That's almost a tongue twister, but I like to keep it min max so it's shorter, but I could even add on more. I could say mean equals mean. Now I've got even more, and this NA remove equals true is being applied to as an option to all of the functions in the previous list. So I'm going to clean this up a little bit just because it's getting a little long. So I've got across all numeric variables, do these three functions, and apply the NA remove equals true to all of those functions, which gives us, let's see, that's three functions across three variables. That gives us 9 different columns, which we can verify here. But we don't have to do numeric functions here. We could also, we don't have to do numeric variables only here. We could also do this on character variables. So for instance, if I wanted to know what are the unique values across all of these character variables. So we have things like home world, eye color, hair color. Those are all things that have different sort of character vectors that they could be. And one way I could look up, let's see, find number of unique values in character variables. One way I could find that is just by summary. So if I want to know how many unique values there are, that's extremely messy. It's going to give me a messy output, first of all, because I've got these list characters here. These list variable types here. I could also try skimmer like we used before. Which does, I have to hunt for it, but I can find that the number of unique hair color items, there's 12 different hair color items, there's 31 different skin colors, 15 different eye colors, 4 sexes, 2 genders, 48 home worlds, 37 species. Like that is those are the numbers I want to find, but sometimes this is a very inefficient way to find them. And I see now I have a chat. Oh, it's a private chat though. Let's see. Yes. So ask me this question again in like 5 minutes and I'll work through that example. And then I'll explain to everyone else what the question was. So if I want to find all of these, but I don't want to have to manually go in and find these values, I can use across. So let me just show you first what I would do to find the unique values for one column name. So if I start with Star Wars, I'm going to comment this one out because I know the code output is really ugly. So if I start with Star Wars, I can say summarize the unique values of hair color. If I do that, we're going to get a column that's going to be the name of the function I just put in because I didn't give it a name. And then we get all of the unique hair colors. So we've got NA, blonde, none, brown, gray, black, all of those unique hair colors up to unknown. Now what I can do is add on to this and say, I don't want to know exactly what those hair colors are. I want to find the length of that list. So if I, in front of this, type length, so in this case, I'm saying, take the hair color variable, get the unique values, and give me how many of those there are. We get 13. I could do this in 2 steps also, but it's a little bit cleaner to do it this way. So in this case now, I know there's 13 unique hair colors here, which I can scroll up at Skimmer and find that, where's hair color? Here there's 12, and that's because they're not counting NA. Now, I want to do the same question, but for all character variables. So let me take down my function a little bit, move it down. And the first thing I want to do, because I want to go across all character variables, I want to say is across. So this says do the same thing for multiple variables. And here I can either manually look at my code or at my variables and say I want hair color, I want skin color, or I can use the helper function where, which I used a few minutes ago. I can say where is character. So we're saying it always wants to put parentheses there. So it's what this is saying is across all variables that comply with the character condition. So if it's a character variable, select it. And now within the across parentheses, so you'll see there's across has parentheses, and within the across parentheses is where we're now going to apply the function we want to use across these different variables. So I'm going to paste this inside. And you'll see right now we have an issue. Up here we just said min, and there was no parentheses, there was no specific, besides this NA remove, there was nothing specifically applied to the function that we listed. But in our case, we have unique and length. So we've got two different functions we're wrapping around each other. So in this case, we actually need to use something called the function syntax. And I'll show you in a minute how to do this one in the function syntax so you can see the differences. So the function syntax starts with a tilde. You'll recognize this from facet wrap and another place where we're going to talk about it today. So this says the tilde, like in English, is as a function of. So we're going to say across these variables, do as a function of length, unique, and then here instead of hair color, because we want to say all of these variables, we have to do a period and an X. This period and an X is basically a stand-in for these variables. So whatever's here, apply it to these ones. So let me run that and see what it looks like. I know this is a lot of steps and we're going to keep going through it. Part of your reading is going to go through this as well, just so we can keep practicing the idea. But now we can see that across all the character variables, name has 87 unique variables, hair color has 13, skin color has 31, eye color has 15, etc. So this gives us the same information we got in Skimmer, but only that information. And sometimes we only want a certain limited information. So now let me show you how we would do this function syntax up here above, just so you can see the difference. I'm going to write function syntax. This here is the way that works in a lot of cases, and it's the quicker way, the easier way. However, sometimes because you need things within parentheses or you're doing more complicated functions, you have to use the function syntax. So in our case here, we would do a tilde, and we would say min dot x, because remember, that's how we apply it to those columns. And then here we could give a comma, and then NA remove equals true, because we can now apply it within that function syntax, and then close out the parentheses. So we've got min dot x, NA remove equals true, within the across parentheses within summarize. And you'll see here the output's the exact same. Oftentimes when I'm actually writing across functions, I end up using this one because it's more flexible in the options you're applying and the complexity that it can arrive to. Okay, so one moment. So if I wanted to apply more than one, okay, scratch that. I'm actually going to go to the question that I got in the chat. So the question is that across can apply to calculate the average of, if we're using the cars data frame, sorry, MT cars, could we get the average mileage per different car model? So if we wanted the average car, let's add and aside. So if we're using the mtcars data set, which is always loaded for you, you can always see it by just running mtcars. We can see we've got our different car models and our average miles per gallon. The question is, can you apply to calculate the average mileage per different car model? So in this case, we're already looking at the average per different car model. You can see we've got each of these car models, and this mileage is the average. If we just wanted the overall average for these, we could say summarize mean MPG. And just get the overall average car mileages. If this person wants to give more detail, feel free. But in this case, that you can just use a less complicated version. So you don't need to use across, you could just use summarize. Okay, back to the lesson. Let me catch up to where I am. So all of what we've been doing can also be very useful because we can do this within group bys or in mutate. So if I want to, let's say, take the Star Wars data frame and group by species, first of all. And then now I want to look at any species that occurs more than once. So I don't want any, those species that they just kind of fill into a random episode. I want only species that occur more than once. I can say filter, and n is greater than 1. So this is nothing new so far, except that I'm putting n, which is find the number of rows in that section, greater than 1. So let's look at that first. So now I know there's 9 species that occur more than once. And now I want to know what are the unique sex, gender, and homeworlds across these. So very similar to what I was doing above, I'm going to say across. And then here, actually, I don't want to do where is character. I want to give it a very specific list of the variables I want. So here I'll use a vector of sex, gender, and homeworld. So instead of using a helper function like where is character, I'm explicitly saying I want sex, gender, and homeworld. And then I want to do a function of length of unique, like I did above, .x. And then now I want to add on another variable that I want to summarize. So this is outside of the across function. So the across function goes to here. Just kidding, it goes to here. I have something called rainbow parentheses turned on, which is very useful because I can see that those are purple. So outside of that final across function, I want to say n equals n. So I just want to get the number of original rows for each of these unique groups. So for species that occur more than once, we can see that droids are always one sex, and I believe, okay, someone's asking about the difference between summarize and summarize. The S or the Z, they're equivalent. It's the British or the English spelling. I just use whatever auto-completes, which is usually the S. If I'm manually typing it out, I often use the Z. Some people prefer to use the S because there's less function conflict names. So if I do an S, it will overwrite less things in R. Okay, so we have these species. These are the ones that occur more than once. And droids are always one gender, one sex, but two genders. Gungans are always one sex, but one gender, etc. Then we've got the homeworlds, where they come from, how many of them there are, and how many characters do we have total in that combination. Or sorry, for that species, not in that combination. So you can see that this would be different than me saying Star Wars. Let me do the same filter so it looks more equivalent. And if I said count, sex, gender, homeworld, this would give me a slightly different output. So what count does is it looks at the unique combinations between those groups. and gives you a count. In this case, we've got homeworld of Alderon. I guess I need to add species onto that for it to be exactly equivalent. So in this case, we've got Alina species, which is a male, masculine gender from the homeworld Alina minor, but it's not condensing these to the number of options that are there. It's saying for each option, how many are there? So those are different, and you might have different uses for both of those. One thing I want to point out, though, is you have to be careful with the ordering of these, because if I put n first, it's likely going to overwrite that. Okay, it didn't. But in some cases, especially like if I was using a helper function, so if I was using a helper function that was selecting numeric variables, n is a numeric variable, and then that could cause some errors. There's a lot of like way too pedantic stuff in this lesson that I don't want to cover. We covered how to do multiple functions. We covered how to do names of functions, or how to name our functions in a list, but we didn't talk about how to control the names of the functions we want outputted. So let me teach you how to do that now. So you'll remember, I'm going to copy and paste this down here just so we can keep working off of it. So you'll remember when we did this function, we were looking at all of the numeric columns and we wanted min, max, and mean. In this case, it always put the, let me put this in a comment, the column name, and then an underscore, and then the function name. In many cases, that's fine for what you want, but you might want something more specific. If you wanted, for instance, it to be backwards, put that in a little bit. So if I wanted to have a function name, then a column name, we actually need to add a little bit of code there to tell our function what exactly we want. I'm sorry I'm doing a lot of copying and pasting today. There's a lot of repetitive typing that I don't want to spend time typing. So I can look at the across documentation to look at how do I edit the names in this. So I'm going to write here just so we can see exactly what each of these functions is implicitly. So if I scroll down a little bit, we can see that there's a function. So here's functions. There's calls, and then there's one called names. And so I'm going to do a line break here and look at names. Now, names, you can kind of see here. I'm not sure how well it shows up on your screen because it's kind of small text, but it's got these tildes, just like I wrote here. Sorry, not tildes, curly braces, curly brackets. And these work off of a syntax called glue syntax. You don't need to know much more about that, just that that is how we can call a specific value into what we're trying to type. So right now, let me just show you the default. The default is .call curly bracket underscore .fns. I always think it looks like a person because it's got like a mouth and two eyes, but we've got the column name and the function names. And you can see that that's in the documentation here. So if I want to change the ordering of this, I can remove that and put that after. So I can say do the functions underscore then the column name. I had a feeling it's FN, not FNS. There we go. Okay, so now if we scroll up, oh, interesting. It's breaking my list column. I'm not sure why. Let me try to remove these here. There we go. So it was something with name calling those explicitly. Usually when you're working in a cross, we don't call on them. I was just trying to show you that they're kind of implicitly there. So Now we can see that we've got min height, max height instead. So we've got the opposite. But whatever you put in quotation marks here, you can make this kind of long, and you can add spaces even. We don't like to add spaces to our variable names, but I just want to show you it's possible. So I can say min of the variable height. And now they're really long, so this is not good practice, but you can kind of see the flexibility of this. You can add whatever you want in these quotation marks. So we've got a quotation mark, we've got curly brackets around our function and our column, and that you have pretty strong flexibility there, which is really cool. Okay, so I'm going to do one last little toy example here before moving on to some more advanced versions of this. So I'm going to copy and paste a simple data frame. So this is a data frame that has the X column of 1, 2, 3, the Y column of 1, 4, 9. Nothing special, just a toy data frame to work with, you can see. Now, if I take the data frame and do summarize, which again, you can do this in mutate, not necessarily summarize. Across is very flexible. I want to take the n first, so that would give us how many variables there are, or how many rows there are, sorry. And then I want to take the across, where is numeric. Remember, we don't put parentheses on the end of that, even though my fingers really want to type them. And we want to take the standard deviation of both of those. You'll see I'm going to get an error because this is what I was trying to point out earlier. And n is then a variable that it's trying to add on the standard deviation for. So this, what I've written here, is akin to doing, do it a little explicitly. So running that first, where you've got 3, 3, 3, and you can't get the standard deviation of something that doesn't vary. The standard deviation breaks. So you can see there's a reason. Oh, I forgot to add a pipe. In this case, the n is 0. You can't get a standard deviation of something that doesn't vary. It's a 0. It doesn't vary. So in this case, we might want to instead add on n to the end of this, so that we can add on the number of groups. I think you could do that with mutate also, without, messing up your ordering, basically. Just with all dplyr, ordering is important, and each thing you add will be added on to the last thing. Be careful with your ordering, long story short. Okay, so useful instances that you might actually want to use now. First is, how do I find things that are not missing? Show me the rows with no missing values. This sounds easy, but it actually can be quite repetitive. So to do this, we can use Star Wars. And within filter, we can say across everything. So here, this literally just means everything. Take all the variables. You have to be explicit about that. And then we can add a function, which is a function of is not missing. And the reason we can't do this one without function syntax is because we have that explanation point in front of it. We have to use function syntax with the explicit.x. So if I run this now, I'm getting a total of 29 rows. If I run just Star Wars, I had 87 rows. So a lot of those rows had something missing. I could see that exactly by just taking out the explanation point. Okay, well, that logically works because you cannot, not everything is missing on every variable. I think you get the idea though. We can also, sorry, I'm reading through my example and I don't like it. let's walk through this one and then I will decide whether this is a useful example or not. So from the Star Wars data frame, we can do something that we're going to learn about later today called distinct. It's very similar to unique, which we were using a few minutes ago. So if I call distinct here and just say distinct, let's say hair color, just to show you what distinct does, it's going to show me very similar to what unique did earlier. But instead of doing that, I want distinct across the variables that contain color in the name. So now it's selecting 3 variables, hair color, skin color, and eye color, and it's giving me the distinct combinations in this case. I can do that and then arrange it by hair color and then skin color. So you can see for hair color, the only combinations there are auburn hair color with fair skin. Auburn hair color always goes with fair skin, it looks like, with blue or blue-gray eyes. However, to do that same thing, and this is why I said I don't know if this is actually useful, I feel like we can just do Star Wars count. And let's see if we can do count across contains color. We can. And so I would do this instead. I feel like that's a lot more straightforward, but we had a worse example in the reading. Yeah, so I mean, even within count, you can add on other options to that variable, like sort equals true. And it's going to sort it by n if I do that. But I don't like that because I like to sort it the other way. But I want to show you that that's possible. Okay, now we're going to do an exercise that I'm just going to walk you through. We do a lot of exercises in the lab on Thursday. And so we're going to calculate the median for each numeric variable for species and gender. So if you all could help me out loud while we write this, I think that would be the best use of our time. So we can have Star Wars. I don't know why I want to type stars so bad. So Star Wars. So if I want to calculate the median for each numeric variable for each species and gender, what do you think the first thing I need to do there is? So I'll give you a hint because we haven't worked with this a lot today. We're going to use a group by species and gender. So now is where we're actually applying the new material. So we've got summarize. And now we want to summarize the median. That would be the function for each numeric variable. So how do I select all of the numeric variables?
Cross.
Thank you, Ash. So across. Now what do I need now?
Is number.
Perfect. So we want to do across where is numeric. And you have to be careful with those parentheses. They really want to be added. So now what do I need to add now if I want to do the median for all of these?
Median.
Thank you, Raphael. Do I need to add anything else here, or is median okay by itself?
You have to add the tilde.
Yeah, okay, so we can do it that way. We can add a tilde, median of x. We can also add NA remove equals true, because this data set has a lot of NAs in it. And there we go. So we've got the species and gender, and for each of those, we've got the median height, mass, and birth year. Pretty great. Thank you all for helping me write that. Okay, I don't like the next exercise, so I don't want to do it. I want to move on to case 1. So if you have any questions regarding across, speak them now because we're going to move on to case 1, which is behind my face. So case 1 is going to be a little bit of a breather. Across is a lot of information, and It's hard to remember the syntax, I find. It's very useful, but it can be frustrating. It looks like Ash has a question. Ash.
Why the last question, even you used MA remove, you still have MA in the birth year?
So in this case, it's because even though we removed the NA, there is, across all of the observations of masculine Alina, there are no birth years. We don't know the birth year of any of them. So let me see. If I add n equals n for the one masculine Alina, we don't know the birth year for it. So it can't take the median of a birth year when there's no birth years there. But that's a really good question.
Okay.
Same with the mass of the Chagrarians. We don't know we don't have any information on those. Good question. So yeah, for the ones that it was able to calculate, it ignores the NAs, but if there's only NA to work with, it's going to be NA. All right, case when. Case when is a very useful variable. If you've ever heard of if-else, some of you may have backgrounds that would have exposed you to the idea of if-else. This is a vectorized version of if-else. So there is an if-else in R. Basically, it says if I have 10 students in class with me, then professor smiles. If else, professor's sad. It's kind of this, if this condition, do this thing, otherwise do this other thing. Now, what's really great about case when is it extends this if else idea to having multiple conditions. So I can say, if there's 10 students, professor smiles. If there's 9 students, professor smiles but smaller. If there's 8 students, professor gets grumpy, whatever it is. You can have multiple conditions in a row, and they can be not necessarily based on the same variable. So it could be if this other thing. So if it's sunny outside, you can have a lot of things built onto each other. So let me show you what this actually looks like in real practice. So I'm first going to start with a kind of toy example that's used a lot in algorithm development. You don't need to really understand this too in depth, but I'm going to create a vector of x of the numbers 1 through 16. So now if I run x, it's literally 1 through 16. And I'm going to just run a case when to show you really what this is doing, and then we'll apply this more to our dplyr case. So the case I'm going to use is basically this question of, it's called Fizzbuzz, and I know where this comes from in algorithm development, but I don't know who came up with it. Basically, the question is, well, sorry, I'm being pedantic. First, I'm going to do just a very simple thing here. You always start with the most specific condition first. So if x is less than 5, we have another tilde, which means as a function of, in this case, I kind of think of it as apply. So apply less than 5. You can apply whatever you want. I'm going to apply less than 5. If x is less than 10, we're going to apply less than 10, then a comma, and then anything else, whatever else you want to catch, is just true is a function of, and then I want the actual number. And so here I know I'm going to have to write as character x. And this is because if I don't write that, it's just going to come to NA because you can't put characters and numbers together. So let me run that to show you exactly what I just did. So remember, these numbers are 1, 2, 3, 4, 5 through 16. So the first number is less than 5, second less than 5, less than 5, less than 5. Then number 6 becomes less than 10 up until we have 10. 10 is not less than 10, it is 10. So it's just going to be 10, 11 through 16. Now let me show you this a little bit more complicatedly with the Fizzbuzz problem. Fizzbuzz, the question is basically, if a number is divisible by 3, print out fizz. If it's divisible by 5, print out buzz. But if it's divisible by 3 and 5, print out Fizzbuzz. I don't know why they came up with this example, but we can actually build out code to test this with our 1 through 16 vector. So
A
I can
question
run-
real quick.
Yes.
Can you please repeat what you explained for the true as character?
Yes. So let me just run it without that. Let me just say X here. So if I just run this, because these first two have quotation marks around it, it knows it wants those to be characters, but X is not a character, X is numeric. And so when I try to put numeric numbers on it, it's going to say must be a character vector, not an integer vector. So we add as character just because I explicitly want it to say those numbers, but I could also just even remove all of this and it would just leave NAs. So basically, like, there is no condition matching this, so nothing. Hopefully that helps explain it. So now we've got fizz equals 3. I'm just going to say equals, but by equals, I mean is divisible by 3. Buzz is divisible by 5, and then fizzbuzz by 3 and 5. So we're going to do something called the mod, which I believe stands for modular operator, which is a way to test if something is divisible by something else, which if I'm using the number 9 and I do a modular on 9, so let me do it here. So if you say 9 modular 3, the answer is going to be 0 because modular is basically what's the remainder left over after I divide this. So if we do 9, this is basically doing 9 divided by 3, what's left over. And in that case, it's 0 because nothing is left over. But if I do 8 divided by 3, I should get 0.66. And that's because 3 times 2 is 6, but then I can't get all the way to another 3. So it gives me 2 left over. And that's true. So sorry, not 0.66, 2 is the leftover. So we're basically, to test whether something is divisible by something, we're checking what's left over. I'm going through that quickly. It's useful in very specific circumstances. So what I want to see first is the most specific case. So if X is divisible by 15, because that would be divisible by both 3 and 5. That's the lowest thing that's divisible by both. So if X is divisible by 15, and so now I have to say 0. So modular x15, I don't know the right syntax of how to say that, but if that's 0, so meaning if it is divisible, return fizzbuzz. Then if X is divisible by 5, return buzz. Then if X is divisible by 3, return fizz. And then if else, return the original number. So let me run this and you'll see what it does. So if anytime it's multiple of 3, so that would be 3, 6, 9, 12, you would say fizz, 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 fizz. But then when we get to 15, that's also divisible by 5, so it would print out fizzbuzz. And then same with the 5s. So 5, 5, fizzbuzz. I could do the same thing with a lot longer of a vector, like 1 through 40, and print this out. And this is a generalizable case of if this, do this, if this, do this. Now, as I said, this is a lot more useful when we think about it in terms of adding new variables. So we might have in our Star Wars data frame, we have a height variable, and I want to mark certain people as tall, certain people as short, and certain people as average. Well, that can be pretty, if we're testing another condition, that can be kind of long, but with case when, it's actually pretty straightforward. So let me first select the species, gender, and height. Now, in mutate, which means add a new column, I can say height categorical. I'm going to say height cat, meaning categorical, not feline. And then I can do case when, which we've been learning. And now here, I can add conditions, just like when we do filter statements. I can use less than, greater than, is not, whatever I want. Here I can say height is greater than 191, because I already looked up that number. And that's tall. But if height is less than 167, I think these are centimeters, this would be short, or otherwise just say average. I'm missing my tilde. So now you can see I've got a new column that's average, average, short, tall, based on this other column. This is a great quick way to do this, but what if I don't want to have to look up first what are the quartiles here, or I don't want to have anything pre-designed. I want to say if this is greater than the third quartile or greater than, less than the third, whatever it is. I would normally modify this, but I know some people look at this code. So instead I'll create a new thing. Instead of saying 191, I want to be very programmatic in this. I want R to tell me what is the third quartile here. So I can say quantile. This is what we learned last week. Height is the third quartile. NA remove equals true. You can always do a capital T or spell out true. And that's tall, or less than the first quartile is short. So you can see we get the exact same result, but I don't have to manually type out very specific numbers. I can let the numbers be calculated for me in the formula. And that's very useful. I can also make this really complicated. So if I don't want it to just be based on height, maybe I want it based on height, weight, and whether or not something is a robot or a droid, as you would say in Star Wars. Let me select the name through mass, gender, and species. Just because I know there's a lot of columns here and I want to just show us the correct output. Then I can mutate. Let's call this type. So I want to see whether something's large, a robot, or other. So I can start with case when. And now for my first condition, I want to say if it's really tall, so if the height is greater than 200, or the mass is greater than 200, and again, I think these are metric units, I want it to be large. But if species is droid, capital D, I want it to be robot. Otherwise, just put other. So you can see I can call in multiple variables as long as they're in my data frame to create a new column. So now I've got large, robot, other. I often use this if I want to selectively label things in my ggplot. So if I want to only label very specific dots, because sometimes you have a lot of dots or observations, and you only want to sample, you can just take a sample of them or whatever you want to do. I often use case when because it can give you a label or nothing, and nothing doesn't print.
I have a quick question.
Yes.
If the height is larger than 200 and the mass is larger than 200, but it's a droid, what would appear?
So if both of these are larger than 200, this is the first one that gets written. So if something has already been written, it will be large. If
Exactly,
it's also
like
a droid,
like an if statement. Okay.
yes. So
Okay.
this is the first one. If it's also a droid, it will already have been written large and it won't be there. So let's see. Let me see if I can find an instance without having to sort it. Oh, that's the only one that's really big. Star Wars. Let's just do an arrange here by height. Okay, let's do a descending height. There we are. Any of these droids? No. I'm going to pipe this into a view so we can see that more explicitly. Okay, droid got overwritten. But that's okay because droid didn't get overwritten. It's if it's greater than 200, and that is exactly 200. So there's no cases, there's no droids that are larger than 200. What about in mass? There should be some large droids. No. Okay, so there's no cases that fit that. Let's do greater than or equal to here, just so we can see the exact conditions. So we had a droid that was 200. So you can see it says here large. So the first condition it went through was large, and it got written as large, and it didn't test that again for the other conditions. That's actually a good question. Thank you for asking that. Okay. One aside I have is about row names to columns. Most people in this class are loading your own data using read CSV or other loading methods and will not have row names in your data set. However, there are a lot of data sets that have row names. So to show you what that looks like, there's a data set that's preloaded called state x77, which I think is the year. And so you can see we've got population, income, these are all columns, but there's no column name for the state because that is a row name. If I open this up to view state x77, you'll see when I open it, it also, like the column names, it gives row names. Tidy data does not use row names. We would like that to be called instead state. So this is very useful under very specific circumstances, but I've definitely used it before, and it saves you quite a few lines of code to say instead, take state x77 and then take the row names and move those to a column called state. It didn't like that. Okay, so it says that's not a data frame. Well, let's see. To see what class my data frame is, I can say state x77 under the class question. That's not something I've taught you all because we haven't worked a lot with different data types, but that's a matrix. So because it's a matrix, first, a matrix is very similar to a data frame. I have not told you this, but a matrix is basically a data frame of all one type. So for this x77, this is a numeric matrix because everything's numeric. You could also have all character, but it has to all be the same thing because generally you're working with that with some sort of mathematical operations. We don't want that though. We want this to be a data frame first. So I'm going to say as data frame and then pipe that into row names to column. Okay. This is not being my friend today. Okay, that's what I thought. Yeah. Okay, I'm going to walk you through the errors because this is very common. So I want to make this a data frame and then change the row names to a column. If I just say as underscore data frame, which is the tidy as data frame code, it gives me an error, which now it's not giving me, which says this is deprecated. Please use as Tibble instead. However, Tibbles cannot have row names. This is all like pedantic, but it's important. Tibbles can't have row names. So if I say as Tibble and then do row names to columns, the new state names are 1, 2, 3, 4, etc. And it's not actually giving me the original row names that were there. So we can either deal with the as data frame, which is deprecated. Deprecated just means that the code is there, it's stable, but it won't be improved upon in the future. So we could use that, or we can use the base R instead of underscores, periods. Either one of these would work. I'm going to leave both of them up here. But now you can see the new row names are just numbers, but that's fine. That's very normal. It's just what row number do we have? And now we have a column name state. Again, this is like very specific use cases, but if you need to do this, it's really important to know, so that I'm just trying to give everyone the memory that this exists. Okay. We also have a code called distinct. We kind of talked about this earlier. Basically, if I want to look at the distinct homeworld, I can say distinct homeworld. So distinct basically gives you the unique values of a variable. So it's in a way doing a summarize though, because it's getting rid of all the other data and it's only giving you a vector of the unique homeworlds that are available. You're not getting the names for the states. Did you do as data frame or as tibble? It's possible. Sorry, someone sent a message. If you did as tibble, it's not going to give you the column names, but if you did as data frame, it should, and then you can convert it to a tibble. Hopefully that helps. Okay, so I can also do this over multiple, sorry, my brain, multiple variables. So I can do this over homeworld and species. So I can see for each homeworld, what are the species that live there? And it's going to give me all of the unique combinations. This is, in my opinion, identical to count, except count gives you the number, so it gives you more information. So if I do here count, it's going to give me the exact same. It's just going to also give me the number of observations there. So I find it a little more useful to use count, but sometimes you need to use distinct for other reasons. So for instance, I had a student come into office hours last week, or student hours, which anybody can schedule. The link is on the homepage of our course website. And what they wanted to know, they wanted to look at that Gapminder data set we did for our ggplot lesson. So if I load Gapminder, the Gapminder data, they wanted to know basically how many, inspired by that first question of why are there so many countries in Africa in this data set, they wanted to know how can we get just the unique countries per continent and find the total numbers of continents, disregarding all of those duplicates for all the different years. So to do that, we worked through that. We can start with Gapminder, and then we can take distinct country and continent. So this is get me all the unique country and continent pairs. So you see you've got Afghanistan and Asia, Albania and Europe, Algeria and Africa. And once we do that, we can do the count of the continent to find how many countries are in each continent. So I'm just giving you that as an example of other instances where you could use distinct, because in this case, we had a bunch of repetition because this was a longitudinal data set over many years.
What about if you do count continent without the distinct?
That's a great question. So if I do Gapminder count continent, you can see now I have 624 rows in Africa because I didn't first weed out all of those duplicates, when really there's only 52. Another good thing about this is I think in some years, certain countries aren't there. So a good gut reaction, but it's incorrect, would be, oh, let me only filter this. So we're only looking at 2007 data and then look at how many unique countries there are. But you might be missing some countries because some countries weren't measured in 2007. So this is a great way to get to that answer that the student came into office hours wanting to figure out. Okay, the final part of today's lab. Can I do it in 8 minutes? I think I can. So earlier we talked about across. Across is a version of column-wise operations. That means we have a data frame, we want to go over multiple things in the column and do the same thing. There's also something called row-wise operations. So let me show you an example of why this matters. And first, I'm going to just paste in some data because I'm not going to take the time to type it. So in this case, I've got a data frame called fruits where I've got the fruit name, the height, the first time I measured it, the second time I measured it, the third time I measured it, I've got the width and the weight. So we've just got some data. We've got a banana, a strawberry, and a pineapple, how tall it was 3 different times. what the width of it was and what the weight of it was. Now, what if I want to get the mean height? I just want to know what is the mean of every time we measure that height, because we have multiple measures. I want to know what the average is because I'm conducting an experiment on fruit. So your gut reaction might be, let's go to mutate. Let's do a new variable called height mean and take the mean of height 1, height 2, and height 3. You might notice right now that all of the numbers are the same because we've got the banana is the same mean height as the pineapple. That doesn't make sense. And you are correct if you're thinking that, because this is looking at all of the data for all of the heights across all of the rows. It's obviously not what we want. We want it to only look at these values and get the mean of those values. Only look at these values and get the mean of those values. This is just how data frames work in R. It wants to do all of the columns collapsed together. So this is where you can bring in row-wise. So if I take the fruits and I say, look at this row-wise. Let's just separate this out by row. And row-wise is almost identical to group by. So group by was separating things out by groups. Row-wise is doing the same thing, but basically everything is its own unique row, multiplied times however many rows you have. So I can just run that and you can see it's not a function, it's a data frame. Now it says row-wise here. I can also say row-wise fruits. Using an external vector in selection is ambiguous. That's why. It's fruit, not fruits. Okay, so the issue was I was calling a data frame, not the name of this variable, which I was trying to do. Okay, so now you can see I've got this row-wise by fruit. The word fruit is starting to look very weird now to me, but it's here. And we've basically got a different data frame for each fruit. Now, if I do what I did before, which was mutate. So we're mutating the mean of height 1, height 2, height 3. We could also just say height 1 through 3. Oh. Get rid of the C. It correctly gets the mean of each of these rows individually. So the mean height was for banana 4, for pineapple was 18.5. So anytime you're trying to get more than one thing, even though these are from different columns, we're trying to do it in rows. A lot of students struggle with the difference between row-wise and column-wise. In this case, we're trying to read things from the different rows together, whether we're trying to sum things up together. So let's say you had an index of different measures. So let's say you have a survey. Oftentimes in surveys, you have different questions that are kind of getting at the same concept, and you want to take the average of all of those, or you want to add up, like there's a depression index, and you want to add up every time someone said something, like if there were 4 or 5, you want to add those up. You could use row-wise so that you're adding up for each individual person. I'm skipping some of this because it's not necessarily helpful, but if I want to use something like a helper function and to help me select different columns, I can do that if I load in this other new data frame. So here's just a simple data frame. We've got ID, W, X, Y, Z, just some dummy data to play with. We can create a row-wise version of it with df pipe row-wise. Now we have RF is the row-wise version of that data frame. Sorry, I'm going through this quickly, but I think you'll be able to rewatch and catch up with this. We can then pipe row-wise into summarize, which would be the sum of W, X, Y, Z. This group equals drop just means don't display the group. So we've got total. If I don't do groups equals drop. You can see that it's giving me some group output. In the end, that's not what I care about. What I care about is now, let's say I want to select all numeric columns here. If I just try to do that by default, it's going to give me an error. So what I want to do instead, summarize and summarize are equal, would be total equals sum of, and now here's a funky one, C across. So it's like across from before, but we have to do C across, so we're saying column across because. And then I can say, where is numeric? Is numeric. And so now it's going to find all of the numeric columns, which were W, X, Y, Z, and sum them all together to give us a total column. If I do this in mutate instead, it will add that on to my data frame. So you can see for this row, for this row, for this row. However, if I do is numeric, it's also going to bring in my ID column that I added in. So for instance, with our fruit example from earlier, I'm just going to paste this in and read through the code. We have our fruits. We want to go row-wise by fruit, and then we want to take the mean of heights. But instead of saying above where I have height 1 through 3, maybe I have a lot of heights. I have 15 different measurements of heights. I can do C across contains height, and it will give me the same value I had before. So there are helper functions here that help you extract exactly what you want. The bottom line is this can get complicated. It can get confusing. Keeping row-wise across versus column-wise functions separate, it's also can be difficult. And that's why I separated them out from the beginning of class to the end of class, so that we can kind of have some mental division between the concepts. Okay, so homework. Oh, where did I go? For Thursday, you've got some examples of column-wise operations and row-wise operations. There's no textbook chapter of this because, as I said, it's all very new. So I just want you to go through these guides and run through some of these examples, preferably typing them out by hand because that's better practice to understand each period, where they go, etc. You don't have to do all of them, but I think it gives you a really good grasp of what's going on. And then anybody who has like 3 minutes to stick around, I'd love for you to try out the possible new video tool we can use for Thursday's labs. I find it a lot more fun. So I'm going to paste the link in the chat. And if you have like 1 minute just to log in and see if it works for you, I would love that, because we can't use it if it doesn't work for everyone. But it's a lot more fun than Zoom. So you're welcome all to leave. I know I have office hours with someone in 10 minutes. So I will meet with them in 10 minutes at the link that the office hours was saved to. And yeah, if everyone can go to this Gather Town right now, that would be great. I will be there if you have any questions for me. Thanks, everyone.